One-way ANOVA, Welch is ANOVA, Post-Hoc ANOVA too. Kruskal-Wallis, it's the bread and butter, baby. What's your
Ciao, Bio 6611. In this lecture, we're going to discuss the Kruskal-Wallis Test, also known as the Nonparametric ANOVA. We'll first introduce our example to look at and motivate why we may be interested in using this nonparametric approach, and then walk through an example of the Kruskal-Wallis test and an equivalent post-hoc test. So again, let's revisit our motivation. The one-way ANOVA test we've previously discussed can be used to compare the means of multiple J groups, where J is greater than or equal to 2. However, it assumes that each population is normally distributed. However, what if that assumption is not valid, or we think there may be some reason where it's not appropriate? Well, one option we've discussed previously in the context of regression is a transformation of the outcome. For example, we could take a log transformation for y, and maybe that would address some concerns. Another approach, though, is to try to throw off these distributional assumptions and use a nonparametric approach, such as the Kruskal-Wallis test, which again is commonly known as a nonparametric ANOVA. Like our previously discussed nonparametric tests for two groups, the Wilcoxon rank sum or the equivalent Mann-Whitney U-test, the Kruskal-Wallis test is just an extension of that Mann-Whitney U-test approach to multiple groups or more than two. And the hypotheses follow along in a very similar way. For example, we always have this format which is appropriate and true for what it's being tested, which is the null hypothesis that the mean ranks of all groups are the same, in comparison to the alternative that at least one group has a different mean rank. Equivalently, we can think of this as a null hypothesis that the samples come from populations with the same distribution, or the alternative being at least one sample as a population from a different distribution. An important thing to note, just like we stressed previously with our two-sample nonparametric tests, is that if and only if we assume the shapes and scale of the distributions are identical for each group, can we state that it's actually a test of the medians. If we are unable to make that comparison or are uncertain about that assumption, we really should focus here on that being a test of the mean ranks of our groups. Because we introduced the idea as well for the follow-up question, if the global test shows there is a significant difference in at least one group, we have similar post-hoc testing we can do for the Kruskal-Wallis test. In this case, we'll specifically look at using Dunn's test, which can account for the nonparametric approach of our Kruskal-Wallis nonparametric ANOVA. This was something we saw previously, noting its connection to the Bonferroni correction for the post-hoc testing for the one-way ANOVA that assumes normality. But in this case, to help account for the nonparametric nature, we have a specific SAS macro we can use, while R has some built-in functionality to automatically address this question. So let's now turn to our example and walk through how we can conduct the Kruskal-Wallis test and interpret our outcome, or our output. We're going to use that motivating example we've been working with in the context of ANOVA, but we're going to assume in this case we're not comfortable assuming normality. Here we're now summarizing the mean ranks we have for each of our groups, which we're just designating here in this table, R bar, and we see that the mean rank increases as the smoking status increases as well. And here, the first place rank is the highest birth weight, going to the last rank, or a higher rank, indicating someone has a lower birth weight. Hence, the heavier group having that lower birth weight in pounds. The code to implement the nonparametric approach in SAS with the post-hoc testing is a little more complicated since we have to implement the macro, but we can note generally we can do this proc npar one way to do our Kruskal-Wallis test, and then we can use this little chunk of code here to implement the macro that we have available on our course website. In R, we can use the desk tools and stats packages instead to do this, where we can first read in our data, then use Kruskal.test in the stats base package to implement the nonparametric Kruskal-Wallis test, and then we can use the Done test from the desk tools package to implement the post-hoc comparison of our mean ranks for the pairwise comparisons. So let's take a look at what the output looks like in R and note that it's going to be pretty similar information-wise to a lot of what you get from your SAS output. Again, focusing first on that global test, the Kruskal-Wallis output. What we see here is that it gives us the chi-squared statistic calculated for this comparison, the degrees of freedom, and of interest ultimately here is the p-value. In this case, we can make the conclusion that since p equals 0.018, and that's less than 0.05, we reject our h naught, and we say that at least one group has a different mean rank. Of course, this may lead us again to that follow-up question for a post-hoc test, which is, well, what group or groups are different and have those different mean ranks or different potentially underlying distributions in their population? At this point, we could run Dunn's post-hoc test on our data, and we see here that we have our pairwise comparisons based on the mean rank difference. What we can see here is that there is only one comparison in this non-parametric approach for post-hoc testing where we see a significant difference. Like before with the parametric post-hoc test we saw, the only significant difference is between the never or non-smoking group in the first trimester with the heavy smoker group, so the most extreme comparison. With all other pairwise comparisons accounting for the fact that we're doing multiple tests, having a p-value greater than 0.05 and not falling below that threshold for significance. And so with that, this concludes our discussion of these tests that focus primarily on comparing the means or the mean ranks between different groups, and we'll turn our focus in the following weeks again back to the more general regression context where we can also address or adjust for continuous variables and other types of categorical variables simultaneously, in addition to our one-way ANOVA or our non-parametric one-way type ANOVA for the Kruskal-Wallis test.